Welcome back, students. We're going to continue where we left off, talking about carboxylic acids. Last discussed ways to make them and the properties of them. The ways to make them including oxidation, a lot of oxidation of the alcohols, double bonds, and triple bonds, and oxidation of the functional groups of benzene. Talk about a few other ways to make them before we get to the reaction. Now you could do a Grignard reaction on carbon dioxide. So let's just look at that hypothetically. So Grignard, remember, we form that by mixing magnesium in a diethyl ether situation into an alkyl halide to form our Grignard. Now this Grignard, remember, likes to attack all sorts of carbonyls. It will attack all sorts of acidic groups too. So we cannot simply fling this onto an acid. But we can possibly attack CO2 itself to form a carboxylate. Now, with that in mind, if you add some dilute acid, then you can protonate that carboxylate, and suddenly you have a carboxylic acid that is essentially one carbon chain longer. Now, I won't say that's the most common way to make it, but that is definitely a way. But remember, we can also, what this guy's new. We kind of did this before. Remember that amines and imines, we could replace those with alcohols, and we could turn alkenes, or we could turn ketones into imines and back. Well, we can do something similar with nitriles. So that's, remember, a C triple bond. We can first form a nitrile using SN2 reaction mechanism, and then just use acid or base hydrolysis to exchange this. So we just let's start with some sort of primary halide, and then SN2 conditions, and use cyanide. And we're going to kick that off and say, we have R, C triple bond C, C triple bond A. So that's pretty easy. Now then, here's what is new. We use acid and water, or base and water. It doesn't really matter. Well, actually it does matter. But long story short, it just depends on whether you have a carboxylate salt or an acid at the end. If you acid pronate, the byproduct is you form ammonium and your acid. So you'd form, RCH2 C double bond O OH and ammonium, because you would keep protonating everything involved. If you did base, you would be carboxylate CO minus, and of course you'd have ammonia as the byproduct. So it all depends on acidic or basic conditions, but really you need to not overthink this. It's the same thing we learned in general chemistry, in that acids will be protonated, the bases will be protonated in acids, acids will be deprotonated in bases. So as long as you remember, carboxyl is a weak acid, carboxylate is a weak base, You go, oh, do that. Same thing as ammonia is a weak base. Ammonium is a weak acid. So let's look at some of the reactions of acids and their derivatives. In fact, we'll like these so much that the next chapter, which won't be on this test, but the next chapter is all about carboxylic acids and their derivatives. So the first thing we're going to look at is nucleophilic acyl substitution. Because it's essentially where this is a big part of next chapter, where one group, one nucleophile will replace another on this carboxyl group. We kind of talked about this. This is how we make acyl chlorides. Essentially, we add a nucleophile, and we're going to kick off one functional group and replace it with another. So, like, oh, I could nucleophile hydroxide and kick off chloride. So, in fact, we can actually we can do this to attack all manner of these. We could attack this X could be a hydroxy group. This X could be a halide. This X could be an anhydride. Anhydride is just a dicarboxylic acid formed into a diether. So essentially, this is our X. This is our X. This is our X. We could use this to attack an ester. Our X. We could use this to attack an amide. All these are such derivatives that we will talk about next chapter. But all these could be used, so we exchange one for the other under certain conditions. Now, most of these are going to be done either with an acid or a base, but conditions and mechanism depend on what nucleophile you have. So you have to have slightly different conditions depending on what you want to add. So say you want to form a acid, we can do the basic hydrolysis of an ester. So the basic hydrolysis of ester. So basic hydrolysis of ester. That in its name tells you everything you need to know what we're doing. So we're attacking an ester. We're using base, and we're splitting with water. So lysis means to cut. So hydro is water. So cutting with water. So the mechanism is as follows. I'm going to go ahead and clear this so I have plenty of room to work. I hate to. So mechanism is as follows. So we start with our ester. And we have our base. We have the lone pair doing the attacking. Remember, the electron pair, Lewis bases attack the acids, not the other way around. So as that attacks, this is going to kick these electron pair up. So we have right here O minus, O R prime, O H. Now here's the tricky part. This is going to this negative charge lone pair is going to swing back down. And this is going to kick off one of these good leaving groups. Keep in mind, hydroxide is a good leaving group. You don't have to be like, why are we always kicking off the ester? Well, we're kicking off the ester because if we don't kick off the ester, we're not progressing. If you kick off the hydroxide, you go back to your starting materials. And we have not progressed anything on the cycle. Remember, these reversible things, we have some of this and some of this. Our goal is to reach a point where we can force it to irreversibly get to a point where it doesn't want to go back. If it doesn't want to go back, then we've achieved an irreversible step. And if we do that, that's where we get our product. So the next step is also reversible. So from our acid, from our carboxylic acid, our acid. Now the thing of this is, unlike that structure, that was not acidic. This structure is acidic. So this OR minus can now attack. It could attack the carbonyl as a nucleophile, but it's much easier to attack the. Oh shoot! It's much easier to attack that acidic proton. So the byproduct of this irreversible step is we form a carboxylate salt and an alcohol. Now that alcohol will not be a particularly good nucleophile. We all know that a neutral alcohol will always be a weaker nucleophile than a charged compound like hydroxy or oxalate or some sort of RO minus. So with that in mind, this is not particularly going to go backwards. So this guy is not going to reattack that guy and act as a good nucleophile. So at that point, we've formed our product. Of course, we don't always want the carboxylate salt. We don't want the carboxylate salt. So at this point, we can add an acid. It doesn't actually have to be an acid. This could be presence of water or any other sort of acidic source. And of course, you're going to reform our carboxylic acid. And of course, our then base. We have more base that we can now use to form the product. So keep going. Now you could do this in acid. It's just going to have to follow a slightly different mechanism as it does this. Let's look hypothetically what would happen if we're doing this in acid. So we're just going about it a slightly different way. Because remember, the lone pairs attack the Lewis acids, not the other way around. So in the presence of acid, we're going to go, oh, lone pair attack here. Form R, C plus O, R minus. Now, from there, water can reversibly attack here. Clean that up. Once again, reversibly, so we have our tetrahedral sp3 hybridized carbon intermediate. Plus. Now here's where it gets a little trickier, in that essentially we have a small little rearrangement. So we have this there, and this going there. So we could get some sort of like intramolecular rearrangement where that hydride is shifting onto the alcohol. Oh, no, sorry. Shifting onto the alcohol, and we're reforming. So now here's where it's like, okay, so we have OH plus, and our alcohol. And then finally, well, in the presence of water, that's not really stable. We can then deprotonate that. So it's just a different way of doing things. It's whether we attack the carbonyl first or we attack the carbonyl second. It's just a different way of looking at it. So, okay, so now this is a good one. Fischer Esterification. It's a way to make esters out of an acid and an alcohol. Of course, this is essentially the opposite of what we just did. It's possible to push it this way. It's just you need the right conditions. So essentially what the Fischer Esterification, it's just O prime OH. It's all these steps are reversible. It's just how reversible are they? So we can push this guy back here. It's once again, all these guys are essentially in equilibrium. All these guys are in equilibrium. So for example, if I have, how do you favor formation of products under equilibrium conditions? Well, anytime you use an excess reactant, you can push it towards equilibrium. So that last one, when we used base hydrolysis or acid hydrolysis, we could have an excess acid to push that towards products. So it's going to keep pushing it that way because we have a lot of acid in there or a lot of water in there. Now this one, with its uses the same catalyst, uses acid and water. How would you say maybe get this, force it to products? Well, you could use an excess amount of alcohol to force this to products. You could have a way of drying up your water as it's being formed to remove the products. Le Chatelier's principles say we shift towards the change. So if I add reactant, I'm going to shift away towards products. If I remove a product, I'm going to shift towards the products. So there is a way to beat equilibrium. You just have to be clever about it. as scientists have been clever for the last many hundred years of how do we get around this. The mechanism going to be very similar, very, very similar. So step one, we're going to add our acid. We're going to have our, oh no, here's our positive acid. Now, this is very important that we do that, because otherwise this guy is going to be a very poor nucleophile. It's not going to be a strong enough nucleophile to add directly to that carboxylic acid like base was. So we had to weaken this guy, this group, further destabilize this group in order to make this capable of nucleophilic attack on that position. So from there, once again, we have our intermediate OH, OH, OH plus R. And then from there, we can then deprotonate that with another, this guy taking that. So that's a reversal reaction that gives us this ugly guy. OH, OH. Scroll down. OH, O, R prime. In the presence of, oh, we have now R prime OH2 plus. Now from there, another equivalent of, from this guy. I'm going to scroll down. I didn't leave myself enough room. From this guy, another equivalent of acid can deprotonate this. Not deprotonate, then sorry. I mean, another equivalent of acid. If I add the acid here, this leaves and we just essentially reverse. So that's not something I even need to consider. I mean, it happens, but if it happens, it moves us backwards. So we don't usually consider the reversible steps of the non-productive steps. So from there we have our RCOH2 plus, a good leaving group. So we can move that down, kick that off. And so we've reformed this guy, ROH plus, OR prime. And from there, more alcohol acts as our base, deprotonates that. So once again, in a reversible step, all these steps, all reactions are really technically reversible. It's just the question is, how easy is it to go backwards? If you form a solid, usually not really easy to go backwards. If you form a gas, it's usually not easy to go backwards. These guys, they're all in solution. You can't really go back, you can't really separate these guys in solution. So that's why all these steps are really reversible. Even the last one, the base hydrolysis, was still, all of them were technically reversible. It just, some of them are a little bit higher energy states. There's a greater energy in the transition that is not really super reversible. Okay, so this this Fischer esterification is really two steps. You can break it down into one, the acid catalyzed alcohol addition to the carbonyl, and then acid catalyzed dehydration. So we're just adding the alcohol as a functional group as step one, and then dehydrating with step two. As I said, this is equilibrium reaction, usually with a very small K constant. So that means it's really tough to form your ester. So even with primary alcohols, it's really small K. It's even lower with secondary and tertiary alcohols, where it's the more sterically hindered, makes it a bit harder to attack. So as I said, how do I drive it to the right? Large excess of reactants, or by removing the product. So we either add a ton of alcohol, which is one easy way, or so like alcohol as a solvent. If I did this in ethanol as a solvent instead of water, we're going to have like an overload of ethanol, which is going to force this to the right. Or I could distill out the water, so boil it out as we go. Or even using a drying agent like magnesium sulfate or molecular sieves or something that's going to essentially remove that product as we go. Because notice on those stepwise mechanisms, I didn't use base or water to deprotonate that. I used the alcohol itself. Alcohols are weak bases to some extent. So they can deprotonate those under certain conditions. So we're essentially driving this all to the right. It'd much rather end up as the acid than the ester. But we can show our mastery over nature and force it one way or the other. Okay. Now we can esterify with diazomethane. That's another way. This one is not reversible, and you'll see why. It's not reversible mainly because remember, if the products are no longer in solution, it is a pain in the ass to put them back. So diazomethane. Remember, what the fuck is diazo group? That's that double nitrogen group that we did a lot of reactions with on that benzene. So if I make diazomethane, diazomethane, I can essentially say CH2 and CH2N2. Diazomethane. So what does that look like? CH2N2, that's going to be C double bond N, double bond N. Plus, minus. So that is a really not super stable compound. If I do this, and I'm going to make sure I don't, it's a non-product solvent, so our dear friend diethyl ether is a good, so we want to add that on, and so it clips right on, and we form OCH3 and nitrogen gas, which leaves. Well, anytime you have the reactant leaving, or one of the products leaving, it really makes it hard to send it back. So why do we not want a product solvent? Well, remember, if it's acidic, you could risk making a hydroxyl group when you don't want to make a hydroxyl group. So we don't want to make a methanol. We want to make a, this is our leaving group. So, okay. So now keep in mind, this is not always the I mean, how does this happen? How does this happen? So the mechanism is kind of a little strange, but it's not too unbelievable. That essentially we are going to protonate this, and that's why we were avoiding making a protic solvent. We're making sure there's nothing to compete with the diazomethane. So our diazomethane has two intermediates, CH, the one I drew, which is CH2 and N plus minus, or we have CH2 and N still plus here, but now it's a minus. This group can depronate that guy, that carboxy group, and form a carboxylate. And our CH3 and triple bond N, which is now a very good leaving group. So the next step is then, oh, this attacks here and kicks off our dinitrogen. And what do we have? We have our methyl ester. And our nitrogen gas. Now, keep in mind, this is excellent yields for small scale, but it is incredibly hazardous in the large scale. Diazomethane is very flammable, and I think it's, if I'm not mistaken, it is also air sensitive. So there's been some accidents in the past resulting in fatalities from doing this, where if you're pulling this up in a syringe and you pull it up the syringe too far, and you get a crack where there's air gap, comes up, flames, you're on fire, horrible, horrible burns all over your body. This is one you want to do small scales. You do not scale up needlessly. So there's ways to do things well, but sometimes they are a little hazardous. So okay, let's keep looking at reactions. Keep looking, we're going good, doing well. So acid condensation with amines. Kind of similar, where most of these guys are with carboxylic acid, so let's say. It'll be very similar to our ester reaction. So R, C, O, just the only difference is now we have a definitely relatively strong base already built in. Alcohols are not necessarily strong bases. So this guy, well, we can right off the bat form a carboxylate and an ammonium salt. That's the first step. It's reversible, but really probably going to end up more on the right side. Now here's the thing. In the presence of heat, we can then drive off water. We can drive off water and kind of push these guys together and form our amide, NH. And we're going to have our H2O, which is going to leave as a gas. Once again, reversible, but as soon as we start losing something as a gas, we're blessed with a semi-irreversible step. Yes, we could probably rehydrate this and force it back, but it's not going to be something like, whoops, I've just screwed up my solution. Now, okay, I'm going to do a couple more reactants and then we'll finish up on Friday. Going to go ahead and talk about reduction. can do reduction of carboxylic acid. So remember, we oxidize to get them there, so we can reduce back down. So the first thing we can look at is reduction of carboxylic acids to form alcohols. Those are obviously going to be the easiest guys to form, because you don't have to stop an intermediate, a very reactive intermediate. So you can just simply go, oh, I'm going to plop in some lithium aluminum hydride source, and then acid. Make sure that's protonated. And then you would go, oh, so RCH2. Now, this is one of those things that isn't fully known. The mechanism isn't fully known. This is a proposed mechanism. But it's one of those really hard things to form. So bear with me. So and the first step is the lithium. The lithium's just the positive charge. We don't need that guy. The aluminum hydride is the important thing. So we have these hydrides right here. And the first thing is this hydride is going to react with the O to form with H to form our carboxylate and hydrogen gas. That's the proposed mechanism. H2. And so that can now lithium carboxylate and Al. Now, this is pretty easy to test for the first step, because I mean you can try to look for the hydrogen gas. Now here's the kind of hard part, is that at this point, this is the likely step. They don't know this for sure. O minus. We have the aluminum trihydride. We see a hydride transfer onto here as we see attaching there and that attaching there. So hydride, we see they think this is what happens. That we see a hydride shift, form the first H. We have an O minus, and now we have an O aluminum hydride. And from there, we see the lone pair shifting down, kicking out this guy to form an aldehyde. Now, the aldehyde, they know exactly what happens to the aldehyde. We know the mechanism. We're thinking, the thing is, we think, oh, we have a lithium aluminum hydrate or some hydroxyl hydrate with a. This is the leading group that they think forms, though they're not really sure. From there, carbonyl, the aldehyde, you can see another lithium aluminum hydride. We donate a hydride there, pick that up. There's our form our RCH2 O minus, and then our acid will protonate that. So we form our alcohol. But essentially, hydride shifts, the mechanism for this is all sorts of crazy kooky, not how you would normally expect it. So this is a mechanism that will never, ever be tested on. If they don't know the exact mechanism, I'm not going to expect you to know the exact mechanism. This does not follow any regular scheme that we normally expect to see. Now there's another reduction mechanism. So we could do reduction by this. We could do it RCH. We could do a borane in THF is step 1. A borane THF complex. And then 2, we use hydronium. So the alternative instead of borane THF is diborane. What, B2H6? No, but why is this important? This pushes us all the way to a primary alcohol. But why is this important is that this is specific for carboxylic acid. This is specific for carboxylic acids, meaning that it will fully reduce an acid prior to even touching a ketone or aldehyde. This will result into very great selectivity. So the example they give in the book is that, oh, I have this benzoic acid with a aldehyde on the other side, or a ketone on the other side. If I use this lithium aluminum hydride, I get 2 alcohols. But if I use the borane, I'm going to get a ketone and an alcohol. So I'm going to fully reduce my acid, but I'm not going to touch my ketone. So the advantage of this guy is that if you only want to touch one functional group, you use the weaker one. The same way as, remember, we might use a different reductant to react with an aldehyde, but not a ketone. And the final reaction we'll talk about before we end is reduction of aldehydes. Reduction to aldehydes, stopping. Well, actually, I lied. I'm going to actually leave that. I'm going to leave that because this is going to involve another reaction. So I'm going to go ahead and leave it there. We'll call it a day, and we'll pick things up on Friday. So we're going to talk about reductions to primary alcohols. So that in mind, I thank you for your attention and say goodbye. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That over and out.